On the 1st of July, 2025, astronomers at the Atlas Observatory in Rio Hurtado, Chile, spotted something strange. An object was tearing through the sky at high speed on a path that made no orbital sense. They named it 3I/Atlas. The designation said it all. The 3I marked it as the third known interstellar object after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. But this was no local drifter. Its hyperbolic trajectory proved it wasn't bound by the sun's gravity. It had come from interstellar space. And after a brief, silent swing through our planetary neighborhood, it would vanish again forever. Astronomers traced its path and found something even more intriguing. It likely originated in the galactic thick disk, a distant, old region of the Milky Way filled with slow stars and ancient debris. In essence, 3I/Atlas is a traveler not just from far away, but from deep time. At its closest, it will pass about 1.8 astronomical units from Earth. That's roughly 270 million kilometers, well beyond the orbit of Mars. No threat, but its arrival raises questions older than our species. Why now? And what does it carry? Some messengers don't arrive with noise. They arrive with motion and a direction no planet has ever seen. This isn't just a comet. It's a sample from a different solar system. For planetary scientists, that's as rare as finding a bottle on the beach with sand from another continent. 3I/Atlas gives us the chance to study materials that weren't formed by our sun, but by another star somewhere far away. Because it's active, emitting gas and dust as it nears the sun, telescopes can study what it releases. Spectra reveal a complex blend of volatiles, ices, carbon compounds, even metallic dust. In other words, this is a piece of a planetary system that's not ours, and it's melting in front of our instruments. Its speed and trajectory hint that it was thrown out of its original system long ago, possibly during planet formation or by a rogue giant planet. That history, embedded in its motion, tells us something about how other stars evolve and interact with their surroundings. And this isn't just a one-time show. If we've now seen 3 interstellar objects in less than a decade, then maybe these visitors are common, and we're only just learning to see them. It's like turning on a light in a room we thought was empty. Studying it is like opening mail addressed from another star, postmarked millions of years ago. When the James Webb Space Telescope turned its eye toward 3I/Atlas, it expected to see something familiar. Instead, it found an object that broke the mold. Most comets in our solar system have water vapor, H2O, as their dominant outgassing material, but not this one. The primary gas surrounding 3I/Atlas was carbon dioxide, CO2, in startling quantities. The CO2 to H2O ratio measured was among the highest ever recorded in any known comet. Alongside that, astronomers found carbon monoxide, CO, traces of other volatiles, and dust containing metal-rich grains. That alone would have made it exceptional. But then came the spectral analysis, and it revealed signs of carbonaceous compounds, similar to materials seen in carbonaceous chondrites, the most ancient meteorites we've studied. Even more puzzling were the hints of aqueous alteration, a possible past exposure to liquid water. But how does something formed in the cold depths of interstellar space show signs of water interaction? One possibility: it formed in a protoplanetary disk rich in radioactive elements, enough to briefly heat its interior. Or it may have orbited close enough to a red dwarf or dying star to warm its core before being ejected. This chemical combination, metal, ice, carbon, and potential hydration, points to a very different kind of nursery. The star system that birthed 3I/Atlas may have had a richer or more chaotic formation history than our own. Maybe its planets formed faster. Maybe it lost a star. Maybe it never formed planets at all. The mystery deepens when you compare 3I/Atlas to its predecessors. 1I/Oumuamua had no visible coma and behaved more like a tumbling slab than a comet. 2I/Borisov looked more like a typical comet, but still had strange compositions. But 3I/Atlas is something in between, clearly active yet chemically alien, not broken, just different. The question scientists now ask, is this the norm for interstellar comets? Or is 3I/Atlas a freak occurrence? If more visitors like this come in the next few years, it might suggest there's a whole population of volatile-rich, metal-laced bodies floating between stars, pieces of broken planets, or frozen archives of systems we'll never see. Sometimes the oddest things are not errors. They're signals from a different rulebook. As 3I/Atlas approached the Sun, Earth's most powerful observatories snapped into action. From Mauna Kea to the Very Large Telescope in Chile, astronomers tracked it nightly. But the real breakthrough came from further afield, from the dusty skies of Mars. On the 2nd of October, 2025, the Mars Reconnaissance Orbiter, MRO, pointed its high-resolution camera toward the comet as it passed just 0.22 astronomical units away from the red planet. This gave humanity its closest-ever image of an interstellar object, a sharp, high-resolution snapshot of its coma and faint tail. Other spacecraft joined in. Instruments orbiting Mars and roving its surface caught glimpses in different wavelengths. Together with Earth-based data, scientists created a multispectral 3D map of 3I/Atlas's dust, gas, and orbit. Observations came in ultraviolet, optical, infrared, and even radio bands, a coordinated campaign across worlds. The European Space Agency and NASA used this global effort to fine-tune the comet's path. Its orbit, previously modeled with a wide error margin, was now refined to within a fraction of a degree. That allowed backtracking its possible origin point with greater confidence. Some trajectories pointed to ancient stars in the galactic thick disk, others to regions near the Scorpius-Centaurus Association, a stellar nursery 400 light-years away. This combined effort, Earth, Mars, telescopes, probes, made 3I/Atlas the most comprehensively observed interstellar object ever recorded. In contrast, 1I/Oumuamua was gone before we could aim most instruments. 2I/Borisov gave us weeks of data. But 3I/Atlas came at the right time during a golden era of planetary observation. More than a scientific triumph, this collaboration symbolized something bigger. It showed that when the unknown passes through, we are no longer just passive observers. We are multiplanetary witnesses, using machines on two worlds to study a third from beyond. To see clearly across space, you sometimes need to stand on more than one world. From the very beginning, 3I/Atlas stirred unease in the scientific community, not because it was dangerous, but because it didn't fit neatly into existing categories. Avi Loeb, the Harvard astronomer who once controversially proposed that Oumuamua might be artificial, raised a similar flag here. Could 3I/Atlas be more than just ice and rock? His reasoning: the high carbon dioxide content, the metallic dust, the strange composition, and the hyperbolic trajectory, all unusual. Add to that the object's behavior, active like a comet, but chemically distinct. It sparked the question, what if this isn't natural? What if it was made? Most scientists pushed back. The comet's visible outgassing, its volatile-rich coma, its dust and radiation signature, all of them point toward a natural origin. Its metal-bearing composition isn't unknown among ancient solar system bodies. The carbonaceous elements fit with materials found in primitive meteorites. NASA's own teams concluded there are no techno-signatures, no artificial elements, no signs of propulsion, structure, or signals. It's just a comet, they insisted. Still, the whispers continue because 3I/Atlas lives in a gray zone. It's not so clearly artificial that we panic, but it's not so clearly natural that we forget. It exists on a boundary, the kind of object that challenges how we define intelligence, how we interpret the unfamiliar. The deeper tension isn't really about this one object. It's about us, our readiness to consider or reject the possibility that intelligence might look like something else. Not a message beamed across radio waves, but a rock tumbling silently through space, designed to be overlooked. Nature makes the rules, but sometimes it lets us believe we know them just long enough to be surprised. Now, let's step fully into the realm of possibility, not fantasy, but informed speculation. Let's ask the question that no space agency dares put on record, but that lingers in the background of every anomaly. What if 3I/Atlas was never meant to be a comet? What if it was built, not formed? Its metal-rich composition, its stable trajectory, its unusual chemistry. What if these aren't just coincidences? What if the volatile ices aren't leftovers from some primordial disk, but a deliberate insulation layer designed to shield what lies within? What if the carbonaceous compounds aren't dust, but encoded organics, chemically locked data, or molecular blueprints? In that case, 3I/Atlas isn't just a wanderer. It becomes a vessel, not a ship but a vault, a probe designed not for speed, but for permanence. Now consider time. A civilization millions of years old, perhaps long extinct, might not rely on fragile signals or electromagnetic broadcasts. Signals decay. Languages shift, but objects endure. Their strategy might not be to shout, but to drift, releasing inert, passive emissaries into the galaxy, scattered like seeds. No propulsion, no guidance, just a trajectory and a hope that one of them, somewhere, someday, would be seen. And then there's the matter of Mars. On the 2nd of October, 2025, 3I/Atlas passed within 0.22 astronomical units of the red planet, a celestial near-miss in galactic terms. Mars, where humanity has rovers, orbiters, and active observation platforms. The Mars Reconnaissance Orbiter with its high-powered camera captured some of the clearest views ever taken of an interstellar object. Could that be random? Possibly. But consider this. If you're trying to maximize the odds of being observed by a technologically aware species, wouldn't you aim near a planet under heavy surveillance? Or at least toward a region where eyes are watching? We have no evidence of control, no beacons, no bursts, no signatures of guidance or propulsion. And yet, if one were designing such a message, the most effective design would be camouflage. Make it look natural. Give it the same materials as a comet. Wrap the archive in ice, dust, metal grains, all the trappings of cosmic debris. Let it slip past unnoticed, unless someone somewhere is looking. This isn't science fiction. It's a reminder of how little we understand about what intelligent design could look like when divorced from the familiar. We imagine machines. We expect antennas, but a true alien intelligence might speak in shapes, in chemistry, in silence. We are used to messages that demand response. But a true probe might be built not to be answered, only to be witnessed. A message doesn't need to be read to exist. It only needs to arrive. And maybe once noticed, it already did its job. Even after hundreds of hours of coordinated observation and the gathering of terabytes of spectral and imaging data, 3I/Atlas remains stubbornly elusive. For every answer we've uncovered, new questions have emerged. Questions that are now guiding some of the most cutting-edge astronomical studies underway. One of the most persistent mysteries is its nucleus size. Hidden beneath a thick, ever-expanding coma of gas, vapor, and dust, the solid heart of the object is nearly invisible. Current estimates range from a compact 200 meters to perhaps over a full kilometer in diameter. But without a clear measure of that core, we cannot determine its mass, density, or internal structure, all of which affect how the comet reacts to solar radiation, gravitational nudges, and its own volatile activity. If it's small but unusually stable, that might suggest a denser, possibly metal-heavy composition. If it's larger and still shows little fragmentation, that challenges our understanding of how such objects survive interstellar ejection and solar approach. Then there's the content of the coma itself. We've confirmed dominant gases like CO2, H2O, and CO alongside metallic dust grains, but that's just the surface layer of information. Scientists are now analyzing high-resolution spectroscopy and polarimetric light curves to search for trace organics, noble gases like argon or xenon, and unusual isotopic ratios. A discovery of non-terrestrial isotopes or compounds not typically seen in solar system comets could radically reshape our understanding of stellar chemistry across the Milky Way. It could even provide a chemical fingerprint of the star system 3I/Atlas was born in, potentially billions of years ago. Another focal point is its behavior near perihelion, the closest point to the Sun in its arc. This is typically when comets become most dynamic, shedding jets, splitting, accelerating, or fragmenting under thermal stress. But 3I/Atlas has surprised astronomers by remaining unusually stable. Despite significant outgassing, there have been no major outbursts or signs of disintegration. This challenges conventional models, especially for interstellar bodies, which are expected to be more volatile due to their unprocessed ices and long exposure to cosmic radiation. Is 3I/Atlas protected by a crust of metal-rich material, or is its internal structure more cohesive than anticipated? Trajectory analysis continues to evolve. Thanks to real-time data from NASA, ESA, and a network of observatories worldwide, scientists are now using gravitational modeling and backward integration to trace the object's likely origin. Some models point to Lyra, while others favor a deeper past, possibly in a galactic thick disk, a region populated by ancient stars and chemically distinct matter. Pinpointing its birthplace could tell us not just where 3I/Atlas came from, but how interstellar migration of small bodies works on galactic timescales. But perhaps most crucially, scientists are already preparing for what comes next. If more interstellar objects are detected, and if they, like 3I/Atlas, are metal-rich, CO2-dominant, and carbonaceous, then we may be uncovering an entire class of alien debris. This wouldn't be a one-time curiosity. It would be the beginning of a catalog of galactic archaeology. Each visitor would offer a slightly different version of how planets form, evolve, and die in other parts of the galaxy. We don't just watch to understand what's here. We watch to know what's coming next, and sometimes what passed long ago. If 3I/Atlas is natural, if everything we've observed holds true, if it is in fact a natural object, an untouched piece of another star system ejected billions of years ago and left to wander the void, then the implications are profound, both scientifically and philosophically. First and foremost, it would confirm that interstellar comets are far more common than we ever imagined. We've missed them, not because they were rare, but because we lacked the tools, the patience, and the algorithms to detect them. For most of human history, our eyes were limited, stuck looking at the brightest, closest, or largest objects. Now, with JWST, the upcoming Vera Rubin Observatory, and even Mars-based telescopes, we are entering an age where not just stars, but tiny fragments of alien systems can be seen. 3I/Atlas is not a beginning. It's a realization that the cosmic ocean is full of driftwood from other shores. Second, its composition